Now we will talk about susceptibility of antiferromagnets. First of all, below the nail temperature, we have each sublattice that is spontaneously magnetized. So with no field, we should have magnetization of the A sublattice equal to minus the magnetization of the B sublattice, so that the net magnetization will be 0. So below nail temperature, each sublattice is spontaneously magnetized such that we have A sublattice magnetization equal to minus the B sublattice magnetization. If we look at the temperature dependence of the magnetization of the sublattices, just like ferromagnets, they will be following the Langevin or in quantum theory, Brillouin function. So as in ferromagnets, the spontaneous magnetization versus temperature follows the Langevin or Brillouin function, the quantum version. So you can see here the sublattice magnetizations M sub A at 0 Kelvin. The magnetization of the A sublattice is number of magnetic moments times magnetic moment per atom. So it's the saturation magnetization, true saturation magnetization at 0 Kelvin. And MB is minus the MA saturation magnetization, and at each temperature below the nail temperature this relationship is conserved. So if you look at the magnetization value here, you will see that these two values at each temperature will be equal, so they will be exactly balancing each other to give a 0 net magnetization. Now, when we apply a magnetic field below the nail temperature, even though the magnetization is 0, there will be a measurable magnetization in the direction of the field. So, although the net magnetization is 0 below the nail temperature, an applied field, magnetic field, can produce magnetization. And here I would like to put a remark about the origin of the magnetic moment per atom in antiferromagnets. In most antiferromagnets, we have the same situation as in transition metal ferromagnets. The orbital contribution is almost entirely quenched, and the net magnetic moment per ion is primarily due to the spin contribution. The orbital contribution is almost entirely quenched, so that the net moment per ion is primarily due to spin. Now, we have two scenarios in the case of susceptibility in antiferromagnets. So first of all, we can have the magnetic field parallel to the sublattice magnetizations M sub A or M sub B. In that case, we talk about longitudinal susceptibility. And the second scenario is where we have the magnetic field being applied perpendicular to the A or B sublattice magnetizations. In that case, we talk about transverse susceptibility. So we will discuss these two in more detail, and then we will talk about powder susceptibility, where we have all directions possible. So okay, for antiferromagnets below the nail temperature, we have the two sublattice magnetizations exactly canceling each other at each temperature with no applied magnetic field. And this spontaneous magnetization of the sublattices follow a magnetization versus temperature curve as in ferromagnets, the Langevin or Brillouin function theory, basically M versus this that we obtain from the Langevin function. And if you remember, Langevin or Brillouin function is basically M versus alpha, which is proportional to the applied magnetic field. So we obtain the temperature dependence from that curve. And at zero temperature, we have through saturation magnetization for each sublattice, number of atoms per volume multiplied by magnetic moment per atom. And when we apply a magnetic field, there will be a measurable magnetization. And this magnetization that we observe in the sublattices in most antiferromagnets is due to spin, since the orbital contribution is quenched. And when we talk about susceptibility in antiferromagnets, we have to discuss two limits. One, where the magnetic field is applied parallel to the sublattice magnetizations, longitudinal susceptibility, and two, where the magnetic field is applied perpendicular to the sublattice magnetizations, transverse susceptibility.